The pose of a robot is completely defined by its coordinate system, which defines its position and its orientation in space. We know that there are 3 axes of translation and therefore also 3 axes of rotation. And we call this 6 degrees of freedom. So in the world, an object has 6 degrees of freedom. It can move along 3 different axes and it can rotate around 3 different axes. When we talk about degrees of freedom of a mechanism, we are asking the question of how many of these degrees of freedom the robot can actively control. So the Epoch robot has 2 wheels, and to start we can maybe consider the robot to have only one big wheel that goes through the center like a big cylinder that rolls. And we can simulate this by setting its wheel speed to 1 rod per second, like so, and see what happens. And you already expected the robot will drive straight, and in this case it drives along the x-axis. Now we can also drive backwards by reverting the wheel speed, and this is not unexpected. The robot now drives along the negative x-axis. We say that this robot in this configuration has 1 degree of freedom because it only can control the x-axis translation. The robot cannot go up and down, and it cannot skid sideways. So there's really nothing the robot can do with its wheels or its motors that will ever make it move along the y-axis, and there's nothing it can do that makes it go up and down. All it can do is move along 1 coordinate axis, so that is 1 degree of freedom. Now this robot actually has 2 motors and 2 wheels, and we can see this by setting one of those wheels to 0. And you see that right now. And I rewind the simulation. What do we expect to happen? The left wheel is set to 0, so the robot will only drive with its right wheel. And something interesting will happen. It actually pivots around its left wheel. And now if you look closer, you can think about a standard wheel as really being only one point where the robot has contact, which is this pivot point here. And the robot now pivots around that point. Now a wheel can not only move forward and backward, in this case along the x-axis, but it can also pivot in place. Now the robot actually does have 2 degrees of freedom. How can we see this? We set one of the wheels to go backwards and see what happens. Now the robot pivots around its center, and we see that it perfectly rotates around its z-axis. So the robot has 2 degrees of freedom. It can translate along the x-axis. It can never translate along the y-axis. It cannot go up and down. Can it rotate around the x-axis? No. Can it rotate around the y-axis? Also no, because it is essentially set to this plane. And now this becomes tricky because of course the robot has a caster wheel, and when you watch it moving forward, you actually do see it pivoting around its y-axis as it hobbles forward. And now we see the robot is actually pivoting around the y-axis, but this is not a degree of freedom that we are interested in when describing such a platform that is stuck to the plane and can only move along the x and y coordinates in the plane and not go up and down. Alright, now you might wonder, how can it ever move along the y-axis? Well, of the world coordinate system. Well, it can do that by maneuvering. So it could go straight a little bit, then it could rotate around the z-axis, and then it could move along the y-axis of the world coordinate system. Will it ever move along its own y-axis? No, because that one will turn with the robot. And we can see this by making the robot go in a half circle. So let's divide the left wheel by 2. And let's save this, rewind the simulation. And now we see that the robot does go in a circle, but the y-axis of the robot always stays put. The robot never moves along it. It essentially combines a translation along the x-axis and a rotation around the z-axis. So this robot has 2 degrees of freedom because it has 2 wheels that are put onto the robot in a way that actually make them complement each other and adding a degree of freedom. Can you think about a way to add 2 wheels to this robot which will not add a degree of freedom? Well, one of them would be if you would put the wheels behind each other, then the robot could only go straight, it could never turn. So we have just seen the standard wheel, which has 2 degrees of freedom. It can go back and forth and it can pivot around its center point where it touches the ground. And we have seen how these wheels can be added to the robot to either add degrees of freedom or not add any, or even constrain them, which is what we see in this example. So this little robot here has a third wheel that is spinning in the air and a new type of wheel which we call a caster wheel. In that case, it's just a spherical steel ball that has 3 degrees of freedom. It can rotate around its x-axis, it can rotate around its y-axis, and it can rotate around its z-axis. It cannot actually translate anywhere, but it can rotate freely and thereby doesn't constrain the robot's motion at all. Now, this robot still has 2 degrees of freedom based on its differential wheel drive, which are the 2 wheels, one to the left, one to the right. And this other wheel is actually suspended in the air. Now, what happens when the robot leaves the platform? Its caster wheel is losing contact, that spinning wheel is hitting the ground, and now it does not add a degree of freedom, but it actually provides a constraint to the kinematics of the robot. So what happens now is the robot cannot move back and forth anymore. It can only spin in place around its z-axis. So at this point, the 3-wheeled robot has only 1 degree of freedom, which is spinning around its z-axis. And as soon as the caster wheel hits the ground again, it lifts the robot up, it removes the constraint and restores the original 2 degrees of freedom of this robot. We now have talked about the standard wheel, which had 2 degrees of freedom, and the caster wheel, which had 3 degrees of freedom. There's another type of wheel, which is called the Swedish wheel, which you can see here. The Swedish wheel can not only rotate around its pivot axis here, but also has rollers that are actuated, and it can essentially rotate around the roller axis. If you drive the Swedish wheels against each other, the robot can move sideways. Now let's watch this again. The reason for that is because the roller axis would drive in a 45-degree motion. These two motions cancel each other out when the 2 wheels here are driving in the opposite directions, and the robot actually performs a sideways motion. The Swedish wheels are very powerful because they make the control of the robot much easier, but they're very costly and of course are subject to dust and other debris that can get stuck in there. So they're not used very much except in kind of clean industrial applications where you can afford wheels like this and maintaining them. Now, we can also talk about the degrees of freedom of a manipulating arm, such as this little KUKA arm here. And this one has 3 motors. One is here, the other one is there, and the third one is here. And so what we can already say about this is that it can have at most 3 degrees of freedom because it only has 3 motors, and each one of them actuates only a single axis. Now, what does it mean to have 3 degrees of freedom for a manipulating arm? An object like this, as we know, has 6 degrees of freedom. It can be essentially anywhere in space and move in any way it wants. The question is now, in how far can a robot N effector like this one change these 6 degrees of freedom? And in this case, the robot actually does have 3 degrees of freedom because these motors complement each other, much like on the differential wheel robot. The robot N effector is able to translate along the x-axis, translate along the y-axis up and down, and then rotate around the z-axis. The IRB 6400 from ABB is a 6 degree of freedom robot. It has 6 driven axes. You can see the base here, a second motor here, a third motor there, and then there's a fourth motor that can rotate the arm, a fifth motor that can swing the end effector up and down, and a sixth motor that can actually rotate the end effector itself. Now, when I said the robot can move along the x-axis, it looks like that, what that requires is solving the so-called inverse kinematics problem. This is something we do later in this class, but now just observe how all the motors work in concert to create a Cartesian motion along the z-axis or the y-axis. The robot also can reach the ball from different orientations, and although I can't demo that right now, you can possibly imagine that the robot is articulated enough to actually touch this ball from any possible orientation. That means from the left, from the right, from the bottom, and so on, and reaching the full 6 degree of freedom in some workspace of the robot.